Hello, everyone. Welcome to today's webinar, Insights to Prepare for and Succeed in Monitoring PFAS, presented by Shimizu Scientific Instruments. I'm Emily Burdett-Katawaki with AWWA, and before we get started, I'm going to go over some tips to enhance your webinar experience. Please close any programs not currently in use, as they may interfere with the reception of our broadcast. Most issues can be resolved by simply refreshing your browser. Also, the windows in your browser are customizable and can be adjusted to your preferred view. Simply click the buttons on your toolbar or drag the edges of each window to resize. Now, we'll hold a Q&A session after the presentations, but questions may be submitted to presenters at any time throughout the webinar. We also encourage you to use the attendee chat to interact and share information with your colleagues. Lastly, if you've met the attendance criteria, your AWWA certificate of completion can be downloaded at the end of our webinar. I also need to inform you the mention of specific products, services, or opinions expressed in this webinar do not represent AWWA endorsement. AWWA does not endorse or improve products or services. Let's go ahead and get started. Our first speaker is Andy Eaton, Senior Consultant and Owner at Eaton Environmental Water Quality Consulting. Dr. Eaton received a PhD in geochemistry from Harvard University and did postdoctoral work at Caltech before spending a 40-year career at what started as JMM Labs, became MWH Labs, and was purchased by Eurofins in 2012 to become Eurofins Eaton Analytical. Andy retired as Technical Director Emeritus in 2020. During his time with EEA, he focused on portable water chemistry, in particular emerging contaminants. He continues to consult for EEA and also is owner of Eaton Environmental Water Quality Consulting, still focusing on emergency contaminants. He is author of numerous articles and has given well over 100 presentations on various aspects of potable water, including many related to the UCMR program. Alicia Beauchamp, Water Quality Lab Director of AWWA, is our second presenter. She joined AWWA as co-op student in 1998 and became a chemist with the company in 2001. During her tenure at AWWA, she held numerous positions within the lab and has been a central leader in establishing the PFAS monitoring program in response to increasing regulations and to provide information to AWWA's customers. Since 2023, she is AWWA's Water Quality Laboratory Director. Alicia earned a master's in chemistry from Villanova University and a BS in chemistry from Drexel University, and is a 20-year veteran of AWWA Pennsylvania. Finally, but certainly not least, Ruth Marhil-Vega is the Senior Environmental Market Manager for Shimizu Scientific Instruments. Dr. Marhil-Vega has 20 years of expertise in environmental chemistry and engineering in the US and Europe, and is the current chair of AWWA's Organic Contaminants Committee. We thank her for her service. She has worked with EPA and the utilities industry to design and execute comprehensive solutions for addressing new environmental and water quality issues, including PFAS, regulated and unregulated DBPs, hope I'm not the first one in the industry to struggle on that one, and other emergency contaminants. Ruth has continued working with environmental stakeholders since she joined Shimizu 5 years ago to make that analytical instrumentation and workflows that enable their successes. She graduated from the University of Valladolid in Spain with a BSc in chemistry, and from the University of Cincinnati with a PhD in environmental science and engineering. Excited panel for us all today. Thank you for being here.
Thank you, Emily. We're looking forward to giving this presentation to you today. Our first talk is basically going to be about the UCMR 5 data as it currently exists and how that pertains to the newly released regulations for PFAS in drinking water. The one thing to bear in mind about PFAS is that over time, we continue to worry about lower and lower concentrations, as evidenced by the trend in health reference levels of PFAS and PFOA over time from 200 to 400 ppt in the days of the third round of the unregulated contaminant monitoring rule to 4 ppt and less today with the publication of the new rule. So this is a one-slide summary of what's currently a 600-page regulation. Bottom line to remember on all this is that MCL compliance is based on a running quarterly average of measurements. PFAS and PFOA both still have MCLs of 4.0 nanograms per liter, also called 4.0 parts per trillion. One thing that's new in the regulation compared to the proposed regulation is there are now individual MCLs for PFHXS, PFNA, and GenX, each at 10 parts per trillion. And the thing to remember there is that it's one significant figure, which means you're actually not out of compliance until you hit 15 for a running average. The hazard index is still in the final rule with minor changes from the proposed rule. First off, you've got to have at least 2 of the 4 compounds present to be out of compliance with the hazard index. Secondly, the denominator for the calculation for PFHXS is 10 rather than 9 that was in the proposed rule. And again, it's one significant figure, so you've actually got to have a value of 1.5 or above to be a violation. And again, the key thing is that compliance is a running quarterly annual average and not just a single MCL exceedance. In terms of the monitoring and compliance, I'll actually directly direct you to a very nice flowchart that EPA has on their PFAS website, but I'll try to summarize it quickly here. First off, utilities must complete initial quarterly monitoring within 3 years of the time of publication of the final rule, and technically, although we've all seen the final rule, it's not yet published yet, so we don't have an official starting date for that monitoring, but I would assume it will likely be sometime in May. However, you can grandfather existing monitoring data such as UCMR 5 to meet the requirement. If you're a large utility serving more than 10,000 and your groundwater system, you have to collect 4 separate quarters of data, and the UCMR 5 program only requires you to do 2. So basically, you have to do 2 more. If you're serving less than 10,000, it's a little bit more complex. And again, I'll refer you to EPA's fact sheet for the details there. If you're a groundwater system and you've used a representative groundwater source approach to minimize your cost for the UCMR 5 monitoring, you're stuck because you'll have to go back and do all of those individual points of entry for your initial monitoring. And again, whether you're a surface water, groundwater influence, or groundwater, you've got to get 4 initial quarters. There are trigger levels for frequency of follow-up monitoring, which are half of the MCLs, and values that are less than the UCMR 5 MCL, which is also considered the practical quantitation limit, or PQL, are treated as 0 for purposes of calculation. However, we highly recommend that you still get quantitative data below that PQL, which a number of commercial laboratories already offer, because that'll give you a better sense of how your treatment effectiveness is, and it'll also tell you, just in terms of compliance, how close you really are to potentially exceeding that MCL. For instance, if your measurements were 4.1, 3.9, 2.5, and 5, the average calculation would still put you below the MCL, but clearly with that 5, 3.9, and 4.1, you're skirting right on the edge of it. You have to comply with the MCL within 5 years, which means if you're exceeding it, you need to install treatment. And it's worth noting that there are a number of states that already have regulations for PFAS, and they're all going to need to modify their rules. But there are some things, for instance, the sum of multiple PFAS to exceed 20 parts per trillion, which exists in some state regulations, which will likely still be there. So pay attention to your state rules in addition to the federal rules. I'm not going to spend a lot of time talking about the UCMR 5 PFAS testing requirements because I assume that most of you are familiar with it. But the bottom line is that we're expecting by the end of the UCMR 5 program, we'll have about 70 to 80,000 sample results available for 29 PFAS. And so far, that represents about 38% of public water supplies that need to sample. And that's actually about the same frequency for the various size categories. So we've got a pretty good handle already of what's going on. So looking at UCMR 5 data itself, what are we actually seeing? Well, there are 10 PFAS compounds that we haven't seen at all yet. And it's worth noting in particular that the 4 that are tested in UCMR 5 by method 537.1 are all still non-detect. And if I were a betting man, I'd be willing to bet at least a nickel that there's a good chance we won't see any of those in the rest of UCMR 5. Or if we see them, we're not going to see more than a handful. Because the other thing is that out of the 19 detected compounds, there are 6 of them that have 2 or fewer detections. So that's less than 0.01% of samples. So in reality, we're finding less than half of the PFAS compounds that we're measuring in the 5th round of the unregulated contaminant monitoring rule. But again, as I noted earlier, this is only representing about 24% of sample results, but it's 38% of public water supplies. So clearly the patterns are going to change slightly as we get the rest of the data. So if we don't see those 10 compounds, what are we seeing? On the left here in red and orange, you can see the regulated compounds, and you can see that just looking at the frequency of detection, that is the maximum value detected in a given public water supply, we're seeing 15% or higher of some of those regulated compounds in large systems and up to 10% in small systems. It's, however, worth noting that if we look on the right in blue, for the 4 compounds that are detected so far at more than 1% of public water supplies, we're seeing frequencies there that exceed the regulated compounds. It is worth noting that although the frequency of detection is high, concentrations in general are relatively low, with 99% of running average concentrations for most PFAS so far being less than 15 parts per trillion each. And it's also worth noting that that's actually lower than the reporting limit that was used in the 3rd round of the unregulated contaminant monitoring rule. So the fact that the concentrations we're seeing are lower than those UCMR 3 MRLs explains in large part why we saw such low frequencies of detection in UCMR 3. So if we break this down a little bit more and look at it by smaller size breaks, the 100,000 plus utilities, the 50 to 100,000, the 10 to 50,000, the 3,300 to 10,000, less than 3,300, what you can see is that in general, the larger the system, the higher the frequency of detection, especially for groundwater systems. But it's also worth noting that even for very small systems, there's significant occurrence compared to most regulated contaminants. And for surface water systems, it's a lot less correlated to system size, which makes sense if you think about it, because the surface water is not originating necessarily in the same region where the sample system is actually drawing from. So you can easily have something that was contaminated from a long distance away impacting it. So let's look at the other compounds that we've detected frequently. And here on the left, you can see the groundwater systems. On the right side, you can see surface water systems. And there are a couple of things to note. First off, we see that same general pattern that the larger the system, the more frequent the detection of various PFAS compounds. The other thing that's worth noting, however, is that particularly for the alkyl acid compounds, as opposed to the sulfate compounds, we're seeing more of those in surface waters than we actually are in groundwater. So again, because they're surface waters, they're likely less sensitive to system size. It's also worth noting that even though we're seeing greater frequencies in surface waters, the concentrations are generally lower than those in groundwaters. So let's actually start looking at the geography of all this. This actually shows the current data set at the National Contaminant Occurrence Database, also known as NCOD. And as I said earlier, we've got data right now on about 38% of groundwater and surface water systems monitoring under the UCMR 5 program. And that represents about 31% of very small systems, 32% of small systems, and 46% of large, where large is defined as greater than 10,000. Small is the 3,300 and 10,000, and very small is less than 3,300. You can see samples are widely distributed across the U.S., so that gives us a pretty good sense that these PFAS results are likely generally indicative of what we'll continue to see. But like they say about the stock market, past performance is not a guarantee of the future. So what are we actually seeing as far as the text? This shows the utilities that are exceeding the 4 part per trillion PFOA and or PFAS MCLs, and what's shown here is actually the maximum value. So technically that's not exceeding the MCL because, as I noted earlier, that's based on running annual average, but it's a pretty good indication of what we'll see. So we've got about 19% of large systems and about 11% of small systems that have hits for one or both PFAS and PFOA scattered across the country, with a lot more along the East Coast and West Coast and the Midwest. And even very small systems, we're seeing about 11% with PFAS or PFOA present. But as I noted, compliance is actually based on the average concentration rather than the single individual exceedance. And what we're seeing for those places where we've got multiple sample collections already, i.e. 2 for groundwater systems or up to 4 for surface water, it drops the number down to about 12% of systems, representing 450 systems across the country, with running averages that exceed the MCL for PFAS or PFOA. And that's about 9% of the national entry points. I suspect the fact that some of this is lower is perhaps due to analytical variability near the 4 part per trillion reporting limit for PFAS and PFOA. So again, it's a good reason to utilize a laboratory that gives you good data below those levels. If we switch from PFAS, PFOA to PFHXS, it's clearly not as big a problem as PFAS and PFOA. But like the PFAS and PFOA, it's a large and small system problem. We've got really less than 0.5% of systems that are likely in violation based on running averages. But there are a fair number, more than 50, that look like they'll have PFH excess running averages exceeding 5 parts per trillion, which means after the initial monitoring period, they'll have to do quarterly monitoring until they can convince their primacy agency that they're reliably and consistently below the MCL. So far, based on the maximum value in a PWS, and it's also the same thing in terms of running averages, that it looks like it's individual MCLs that are driving compliance and not the hazard index. So specifically, about 19% of large systems and 11% of small systems may exceed the EMCLs. We won't clearly have good numbers on that until we've got all 4 quarters of data for all of them. There are 2% of those that, in addition to the PFAS and PFOA, also exceed PFH-XS. There are only a few systems, less than 0.3%, large or small, that exceed the PFH-XS MCL and don't have PFAS and PFOA already as issues. One system may exceed the Gen X MCL, and there are none that only exceed the hazard index. And of course, as we add more sample events, we get a decreased frequency of exceedance. So if we look at the number of compounds, it's clear that, as EPA noted in the rule, if you have one compound, then you're likely to have multiple PFAS present. So except for small groundwater systems, 20 to 30% of systems have more than one PFAS present. And if we look at where those are, you can again see a lot along the East Coast, California, Arizona, with multiple PFAS. And there are about 30% plus that have at least one PFAS present, and 13% that have more than 3 PFAS present. So if you get one, you get more. So what are our conclusions? First off, PFAS and PFOA are clearly a national problem impacting about 15% of systems. It's going to be expensive to remove simply because it's a large number of impacted entry points and systems. PFAS and PFOA clearly look like they're the main drivers of compliance. Other PFAS compounds occur quite frequently in drinking water, but concentrations don't generally seem to be at levels of concern, but it's worth noting that consumers don't seem to care about the difference between detection and concentration. And again, only 19 of the 29 compounds are detected so far. They're all 533 method compounds, but in the final rule, you can actually use either method for doing your compliance monitoring. We'd still encourage people to use 533 because of the data you'll get on other compounds. Large systems have a greater frequency of detection, but small system issues are significant. And finally, the database is going to get larger. It's unlikely that patterns will change in a significant manner. And with that, here's my contact information, and I'm going to pass the ball to Alicia, and we'll take questions at the end of our presentations. Thank you.
Thank you, Andy. Hello, I'm Alicia Beauchamp, the Water Quality Laboratory Director at AWWA Pennsylvania's Environmental Laboratory. I'm going to talk today about lessons learned from routinely analyzing for PFAS. First, some background information. AWWA is part of Essential Utilities, which is one of the largest publicly traded water and wastewater and natural gas providers in the United States. AWWA was founded in 1886 in southern Pennsylvania and has over 136 years of history and experience. It was founded by Swarthmore College professors whose concern for water quality inspired them to build a pumping station for their community. The company is focused on delivering Earth's most essential resource, water, to customers and communities. AWWA provides drinking water to approximately 3 million people and wastewater service to approximately 250,000 people across the 8 states that we serve. AWWA has an environmental laboratory located at its headquarters in Bryn Mawr, Pennsylvania. The laboratory is a cornerstone of our company's work to ensure clean, safe, reliable water and wastewater. The lab consists of 4 sections: inorganic, organic, microbiology, and research. Overall, the laboratory runs over 90,000 water quality tests annually via 30 different analytical methods and is run by a team of 20 chemists, microbiologists, and quality assurance professionals. The samples analyzed consist of compliance samples as well as operational samples that support the needs of the utility. The laboratory holds primary state certification for various methods for drinking water and wastewater in 5 states: Pennsylvania, New Jersey, Virginia, Ohio, and North Carolina. AWWA's laboratory first became state accredited for PFAS in 2017. PFAS are a large, complex group of synthetic chemicals that have been used in consumer products around the world since about the 1950s. They are used extensively by manufacturing companies, military sites, airports, and firefighting training centers. They are ingredients in various everyday products. They have been found in food, water, soil, and approximately 95% of the United States population. It is estimated that about 80% of exposure to these compounds can be from environmental factors and about 20% from drinking water. PFAS molecules have a chain of linked carbon and fluoride atoms, and because the carbon-fluoride bond is one of the strongest, these chemicals do not degrade easily in the environment. AWWA initially set up in-house analysis for Method 537 in November of 2016. This setup occurred after the Unregulated Contaminant Monitoring Rule 3, or UCMR 3, had ended. There was still a lot of focus on the presence of these emerging contaminants at the time, and the decision was made to set up and begin testing for these compounds in-house. When we first embarked on implementing analysis, we were faced with a lot of questions, such as what analytes should we focus on, and how low should our detection limits be. We ultimately decided to move forward and set up EPA Method 537. The method was set up for the 6 compounds that were studied during UCMR 3: PFBS, PFHXS, PFHPA, PFNA, PFAS, and PFOA. We did add the compound PFHXA in 2019. The focus of the method at the time was really on PFOA and PFAS, which are the 2 most common and studied PFAS compounds. Also in 2016, the health advisory for PFAS and PFOA was lowered to the combined greater than 70 ppt concentration. We decided to move forward and implement the lower minimum reporting limits for the method. They were set between 2.2 ppt and 2.5 ppt for the compounds of interest. We became one of the first utilities to be state certified for PFAS in Pennsylvania in 2017 for the 6 compounds. This was followed by becoming state certified in New Jersey for 3 compounds of interest. Between 2018 and 2020, New Jersey, one of the states that we operate in, set maximum contamination levels for 3 PFAS compounds: PFAS, PFOA, and PFNA at 13, 14, and 13 ppt respectively. In 2020, AWWA set a company-wide standard to treat at 13 ppt for 3 compounds: PFAS, PFOA, and PFNA. And in 2022, Pennsylvania announced the regulation of 2 compounds, PFAS at 14 ppt and PFOA at 18 ppt. Also in 2022, AWWA's laboratory expanded its PFAS testing capability by purchasing a second LCMS and setting up and becoming state certified in Pennsylvania and New Jersey for Method 537.1. The laboratory set the method up for all 18 compounds that were included in the method. The target minimum reporting limit, or MRLs, for these compounds was between 2.2 ppt and 2.5 ppt. To date, we have analyzed over 16,000 samples in-house. In 2018, we set a company initiative to proactively test all of our sources. The various types of samples analyzed have been raw groundwater and raw surface water samples. We have also analyzed samples to provide results for various treatment studies. And once treatment systems were installed and operational, we began to routinely analyze performance monitoring samples at these locations. Once the states of Pennsylvania and New Jersey began setting their own MCLs, we were analyzing compliance drinking water samples. We are currently in the process of analyzing samples for the Pennsylvania MCL initial monitoring. As the sample load increased significantly and as technologies advanced, we were able to significantly reduce the time it took to prepare a sample for analysis. In the initial setup, the sample preparation process could take up to 3 days. By upgrading equipment and taking advantage of newer technologies, we were able to significantly reduce overall turnaround times for a PFAS sample. The initial extraction process was slow and could take 6 to 8 hours to extract one full batch. And in 2021, we invested in newer automated extractors that reduced the time to 2 hours per batch. Our older evaporator would take approximately 4 to 6 hours for a full evaporation batch. And in 2022, we invested in a nitrogen generator and a newer evaporator that was capable of evaporating a full batch in approximately 2 hours. Being able to focus each of the methods for specific analytes of interest helped in being able to analyze more samples. Early on, method 537 was optimized to analyze for the 7 compounds of interest in less than 9 minutes. For method 537.1, we wanted to enhance the sensitivity of the method while also focusing on all 18 compounds in the method. Using an updated column for this, the runtime was optimized to be less than 18 minutes. Successfully implementing a pipetting robot into the sample preparation process helped to expand lab capacity by saving valuable analyst time. It became apparent early on with the number of samples we were running and having only one instrument that planning routine maintenance and having a dedicated service was a priority. We relied on having service contracts and keeping up on routine maintenance to prevent any significant downtime. We do our best to schedule any necessary maintenance around times with lower sample load expected. Staffing is also a challenge as state certification requirements can be very specific on who can be considered a qualified analyst. There can be a strict amount of training hours and even a minimum number of chemistry college courses required to become a technical supervisor of LCMS instrumentation. Another one of the biggest challenges of routine PFAS analysis is the potential sources of contamination. From sampling, sample preparation, the lab environment itself, and the equipment used, PFAS compounds are everywhere. Because we are looking for very low detection limits, the smallest amount of contamination can affect analysis. For PFAS methods, you are required to test everything prior to use. When possible, we utilize purchasing large amounts of the same lot number and test everything: SPE cartridges, sample bottles, tubes, vials, standards, and solvents prior to use. You may need to consider replacing all of the PTFE tubing on your system with PEEK, and the use of a delay column is essential. Sampling can also be a challenge as there are many different scenarios and aspects that go into it. A lab can reject a sample if it was not collected according to the sampling instructions. If possible, have dedicated trained samplers or supplied detailed sampling instructions prior to sampling. Do not use blue ice or test it before use. Have a clear field reagent policy. Some states allow samples to be accepted if there was no corresponding field blank collected, as long as it is reported with a narrative, and others recommend that the sample should be recollected if there was no FRB. Some other notable improvements we have made over the years from investing in newer technologies. Overall, we were able to improve our sensitivity and reduce the method detection limits for the MDLs. For example, PFOA was 1.34 ppt and was able to be lowered to 0.64 ppt. And PFAS was at 1.3 ppt and was able to be lowered to 0.75 ppt. Also, overall turnaround times significantly decreased from approximately 4 days to, if really needed, as little as 24 hours. Precision and accuracy was able to be improved upon. RPDs of replicates decreased with the newer equipment and by fine-tuning the method operation. This is a snapshot of our current setup and workflow. Currently, the 4 chemists and the supervisor of our organic chemistry laboratory section are all trained on the PFAS methods. Each trained analyst takes turns rotating through each day. Each of these analysts are also trained and rotate to support other methods within the organic section as well, like HAAs, THMs, and VOCs, The process starts by adding our surrogate solution to the samples and then loading them onto the current automated extractors. We currently have 3 extractors, which allows us to extract up to 24 bottles at a time. Once the extraction is completed, the eluted collected sample is evaporated. In the evaporating step, the sample is evaporated to complete dryness, and this step is followed by a reconstitution step, where the sample is brought back into the liquid form in order to be analyzed on the LCMS. The reconstitution step is where the pipetting robot was implemented. The goal for this equipment was not just to save the analyst's risks from manually pipetting so many times, but it will also save approximately 20 to 30 minutes of analyst time per batch. This allows the analyst to be prepping another step. Once reconstituted, the sample volume of 1 microliter is injected onto the LCMS, where the current runtime for the 18 analytes is less than 18 minutes. The PFAS journey. This is a diagram representing AWWA's PFAS journey. It began back with UCMR 3 in 2013 to 2015, followed by the lowering of the health advisory and setting up in-house testing capability. We installed our first treatment systems in 2017, and by 2018 had a company initiative to test all of our sources. Between 2019 and 2022, we had various MCLs set along with the AWWA company standard of 13 PPT, which all led to the announcement on April 10th of 2024 with the final PFAS rule. Public water systems will be required to monitor for these PFAS and have 3 years to complete initial monitoring, followed by ongoing compliance monitoring. The EPA PFAS rule, as Andy had mentioned earlier, sets PFOA and PFAS MCLs at 4 PPT, GenX, PFHXS, and PFNA at 10 PPT, along with a hazard index for 4 compounds of 1, which is unitless. So what does this mean are the next steps in routinely analyzing for PFAS? For us, there is the potential to be possibly looking to lower our MRLs for our current in-house methods. There will be additional equipment added. Already this year, we just added 1 more automated extractor to our workflow for a total of 4. The sample load is increasing. The load is expected to double from an average of 2,000 samples per year to approximately 4,000 for 2024. Staffing in order to meet the needs of the sample load. We did add 1 more full-time analyst in the organic laboratory section for 2024, which will bring the total number of analysts trained to run the PFAS methods to 6. There is also the potential to be adding additional methods with more compounds. We are currently in the process of phasing out method 537 and will look to implement method 533 while keeping method 537.1. Also, this talk was centered around PFAS testing for drinking water, but there will also be the need for PFAS testing in wastewater. So there could be the consideration of adding method 1633 in the future as well. Overall, we will continue to look for updates and improvements to measuring and analyzing for these compounds. And with that, I would like to say a big thank you, and I would pass it over to Ruth Marfeld-Vega. Thank you.
Thank you, everyone, for joining the presentation, and thank you, Andy and Alicia, for the great talk. As Andy was mentioning somewhere else, we are all together in this. We need to partner, labs, utilities, industry collaborators. And we are getting a lot of questions in the chat, and I'm going to try to address some of them during my presentation because we are going to be maybe running out of time. I'm Ruth Marfeld-Vega, as I was introduced earlier, and I'm the Senior Market Manager for the environmental market at Shimadzu. And I'm going to be covering 3 main topics today. I'm going to be talking about sensitivity, the presence of PFAS in the background, and also I have some additional, I have frequently asked questions lumped together in the last part of my presentation. Sensitivity. Alicia and Andy show the roadmap of PFAS over time and the different numbers EPA put out there over time. But now finally, April 2024, we have a reference value that we can use, and it's the maximum contaminant level. Something that we need to keep in mind, and I'm seeing from the questions that in the audience there are people more familiar with the work in the lab and others that might be less familiar. When we talk about maximum contaminant level, that's very different from the method, reporting limit, method limit of quantification, detection, all those names and parameters that are commonly included in EPA methods. All vendors have different instruments for PFAS analysis, and today's talk focuses on liquid chromatography mass spectrometry. That is the instrument that is required for the analysis of the 6 PFAS that made it into the final PFAS rule in drinking water. As I said, all vendors offer different instruments with different features and different sensitivity. So deciding which one is best for you is going to depend on your goal. As Alicia mentioned earlier, AWWA established different limits before EPA established the federal maximum contaminant level. Also, something that we need to keep in mind, as of today, in April 2024, the methods that are approved by EPA for the analysis of PFAS in drinking water, 537.1, 533, there are some details about the difference between the two methods in the table that I'm showing. Those two methods require the use of solid phase extraction. And what does that mean? When you need to do solid phase extraction, you concentrate the mass of PFAS that is present in the water before analyzing it in the instrument. And that helps in achieving lower concentration, quantitating lower concentrations in the sample. Obviously, when you have to do solid phase extraction, it's going to take more time, more money, there is a potential higher error, but also you are cleaning your sample. So that's going to help with the overall performance of the instrument. And when we think about sensitivity, we need to keep in mind that if we use a very sensitive instrument, sometimes the signal from the compound is going to saturate the detector. And then you are going to have to dilute your sample and re-inject. Again, more time and longer turnaround times. At Simatsu, we've been working on PFAS analysis for many years. And we've optimized methods that we know they are ready to be deployed in your lab. So you can minimize the effort that you need to put up front to make sure that you are going to be ready to start analyzing the PFAS, selected PFAS compounds. We've been doing this work with mid and high sensitivity instruments to demonstrate that you can achieve your goals with the two different platforms. We like to use as smallest volumes as possible, so the instrument stays cleaner for longer time. And specific for 537.1, 533, the methods that we are currently happiest with are 50% shorter than the original methods published in the EPA methods. Some results that based on 537.1 and 533, the plot at the top of the slide represents the MDLs from the two methods, 537 in the darker bars and 537.1 in the lighter color. We use a mid-sensitivity instrument, and similar to the results that Alicia mentioned, the method detection limits are between 0.2 and 1.4 nanogram per liter. The important thing also is that the 6 PFAS that made it into the final rule, the method detection limit is for all of those less than 0.8 nanogram per liter. And there was a question in the chat about milligram per liter, nanogram per liter. Milligram is part per million, 1 in 1 million. When we talk about nanograms per liter, we are talking about parts per trillion, 1 in 1 trillion. So we are looking at very tiny concentrations when we are looking at the PFAS analysis. Alicia also mentioned about 1633 for wastewater, and this is important to keep it in mind, especially within the context of groundwater. EPA published the final 1633 a couple of months ago, and here I have a summary of the results that we obtained for this method. The plot on the right represents only the results from the carboxylic and the sulfonic acid. 1633 has 40 compounds total, but the results were similar across the board for all the targets. Overall, we could achieve up to 10 times better method detection limits in red in the plot than those reported in the EPA method with the black dotted lines. And I want to spend a minute here talking about something that we use when we optimize this method, and is the use of co-injection. You can achieve that with the Maximum CMS. And what's co-injection? When we inject the sample using this approach, what we do is sandwich the actual sample in between different solvents. So we make sure that the physicochemical properties of the mobile phase are favorable for the compounds that we are analyzing. And that's going to help us with improving the chromatography, and it's going to allow us to quantify at lower concentrations with the same instrument. There were several questions in the chat also about PFAS in the background. Alicia mentioned that it's essential to check the presence of PFAS in the background in all the consumables that you use, especially when you open a new batch of consumables. When we focus on the instrument, there are three key elements in this part of the workflow. One is the solvent lines that are used in the LC. Two is the degasser, and third is the delay column. Someone asked in the chat what the delay column is. It's a column that is placed in the instrument before the mixer and before the analytical column. With the use of the delay column, we separate potential PFAS present in the background from the signal of the actual targets in the sample. We've been doing a lot of work to demonstrate that the delay column is the essential piece, depending on your goals, your sensitivity goals. So you can keep your degasser in line, or you can keep standard solvent lines. It's all going to depend on the final sensitivity that you want to achieve. And I have some results here of an experiment that we are doing right now to demonstrate this in the lab. Then we are doing this with the brand new instrument installed in the lab with a standard configuration, the gasser in line, a standard fluoropolymer tubing. It doesn't need to be Teflon. There are other PFAS that are being used in different plastics, in different polymers. So we use this standard tubing. We follow 1633 as method of reference, and we use the standard injection as well as the co-injection, as I mentioned earlier, that allows us to achieve better detection limits. To make sure that the results we were getting were real, because when we are looking at the background, sometimes we are just monitoring noise. We run everything with 7 replicates. And we tested several conditions without the use of a delay column, with a delay column, and we did different injections, null injection. That's something that you can do with the Maximum CMS, and it's a true test of the presence of PFAS in the background, in the instrument and the mobile phases, because there is no external input. Basically, an amount of solvent that goes in the mobile phase bottle goes through the system, goes through the needle, travels through the system until the mass spec, following the same method, the same gradient. And as I said, there is no external input. So if you find PFAS in the non-injection, that's, you know, that is coming from the LCMS or the solvents that you are using. We also injected standard blanks and calibration curves. There are 8 compounds that I'm not going to repeat now listed in the slide. Those are the compounds that we detected during these tests. And the important key message to remember is that none of the 6 compounds that made it to the regulation were detected. And as you can see in the plots on the right, when we install the delay column, there is a separation between the signal in the background and the actual signal of the targets in the sample. This is an example of the results that we got when we vetted 537.1 and 533, where we found less than 4% of the signal coming from in the laboratory region blank when compared with the method reporting limit, and that meets the EPA criteria listed in the method. Moving now to the more generic questions. Something that people ask me a lot is, how can I make sure that my team is ready for PFAS analysis? And one thing, as you saw today, the scientific community has a lot of experience about analyzing PFAS. We've been doing this work for decades in the research environment, but also in the compliance environment. So reach out to your network and look outside the traditional places, outside AWWA, and look for other professional organizations. Also join the AWWA committees. There are 2 for sure that are prioritizing efforts around PFAS. One is the Water Quality Laboratory Committee, and also the Organic Contaminants Control Committee. And as I mentioned earlier, at Shimadzu, we've done a lot of homework to make sure that if you get the instrument installed in your lab, your team is going to be ready to start running the initial demonstration of capabilities. Another frequently asked question, money. We all worry about money and how much all this costs. I created this ROI calculator to help you go through your thought process and decide what's best for your lab. This is not posted publicly, but if you want to get access to it, send me an email or scan the QR code and request in the notes that you want access to the PFAS ROI calculator. What's in the future about PFAS? More methods. We know EPA standard methods are working on direct injection methods, but also more technologies. At the beginning, I mentioned that 6 PFAS that are in the regulation for drinking water are analyzed by LCMS, but GCMS and combustion ion chromatography are going to start playing a bigger role in the analysis of PFAS within the water industry. And with this, I would like to thank you again for joining the webinar. Today, you have my email on the screen. Feel free to reach out. And also, before we take questions, I would like to share with you everything that Shimadzu can offer for environmental analysis. And you can see there are solutions for PFAS, TRC analysis, but all the regulated and unregulated contaminants. Thank you all for your attention.
All right, so we have a few moments for questions if we want to have all of our panel come on. And since it is a brief moment, I will go ahead and remind everyone now that if you submit questions. Questions will be shared with the panel so that they can reach out with more information. So the discussion will continue beyond the live time that we have here. Ruth, we wanted to go ahead and with this final question that we'll be able to ask today, to put it to you. We know that you had kind of a top question that you were looking at. So do you have your top last thing you want to make sure you say amongst those other frequently asked questions? We got many questions, by the way, our audience. We thank you so much for being so involved and sending in so many. Our panel will have much to look at and answer you. I believe that one of the earliest questions we were looking at was, let me find it here. It was near the beginning. We had people who were thinking that they wanted to distinguish between average concentrations. So Jill, thank you for asking, why does the average concentration for PFH, XS, PF, and A or Gen X have to be greater than 14.9 parts per trillion to be a violation when the MCL for each of those PFAS is 10 parts per trillion?
Yeah, the reason for that is EPA has established different significant figures for compliance for PFAS and PFOA versus the other compounds. So for PFAS and PFOA, results are reported to the nearest 0.1 part per trillion, and compliance is based on averaging that. Whereas for the other compounds, it's based on just reporting to the nearest nanogram per liter. So when you do the averages, you actually end up being an average that would be greater than, that would be 15 or greater, as opposed to just greater than 10 per se. If the regulation were set at 10.0, then compliance would mean anything over 10. So hopefully that clarifies it, and it's the same thing for the hazard index. There's actually a very good fact sheet from the EPA on their PFAS website that goes into some of those details if I didn't clarify it adequately here.
All right, and let's go to another one we marked. Looking on the other side, with your 1 minute left here, Alicia, we did have something, a question as high level as, do plastic containers affect PFAS results?
Yeah, so when you're collecting for PFAS, you want to use a certain type of plastic container. What they recommend is a polypropylene container for any type of sample collection. What they don't want you to use is any type of glass or anything like that. So I hope that clarifies that answer.
Perfect, Caroline, thank you for asking that. So I think we'll go ahead and close so that we can end on time today in respect to our attendees' time. But again, thank you for everyone who submitted questions. We are at the end of time, but your questions will be shared with the panel so they can reach out with more information. A couple reminders before you go. If you have met the requirements, you can download your certificate of completion now by clicking the icon in your toolbar. When we close the webinar, a survey window will appear. Please take a moment to respond. Your feedback is very important to us, and it helps us improve our program. And finally, I would like to thank our audience and our panel for joining us today. And until next time, thank you for keeping the water safe and secure.
Thank you, everyone.